it's not, in the end I'm going to show you how you monitor performance, but throughout the session I'm going to talk about what you should do to get the max out of Windows Azure, to get the best performance, right? And why, if you don't do that, you're going to end up having suboptimal performance. So that's focused on performance.
So audio is not correct.
No, it's not set up properly. Sounding like best practice because I said this is what you should do to achieve optimal performance. I can tell you what not to do, exactly the reverse of that, or maybe you do the things the other way. This is the part you should follow, this is the thing you should take care of this, if this is how you should build your application, right? To get maximum out of it. Okay, Anita, I'm going to description of what is performance from an application standpoint. Then I'm going to talk about performance metrics, what generally you measure when you do performance monitoring for an application. Right? And then this is the dense part. The best practices for compute. Compute is essentially the web workloads, the cloud services that we build, and that is the most common part along with storage, the blobs, the queues, and the tables. Right? What is the guidelines from the Azure team and what are some of the things that you should do to extract the max out of your storage? You pay money for that stuff, right? And you can always scale that up, you end up paying more money. So to get the best out of it with the least amount of money, this is what you should do. Right? Caching, there is again a service from in Windows Azure, and how you should use it for some of the things that you take care of while using caching service in Windows Azure. And finally, I will show a demo on performance monitoring, how you configure your performance counters in Windows Azure and how you use them. So this is something like that. Application performance. Basically, it's the amount of useful work that the application does versus how much time and resources it's consuming. Time resources, it could be response time, it could be on what kind of server you want, how many resources you're consuming. You could be on a large XML machine, like 8 or 16 cores, that's a lot of resources. Compared to that, how is your application performing? What's the response time? How many requests per second it's able to handle? That kind of stuff. And that's what we'll see here. Performance metrics. Okay. Response time. Say for a web app, particularly, you open web app and you see how much time it takes to count. When you host those applications in Windows Azure, throughput, how many requests you can handle. It could be workload also, what kind of work it's doing. How much it's churning out, and availability of your application, right? What is the percentage availability of it? Percent time it's available. So those two things are the main things on the metric side. Now, most of people believe you build an application and it's going to take care of everything. You just have to build an application. You don't have to do everything. Build a normal application in Azure can scale indefinitely. It's partially true. Azure proposes to scale to very high levels. You can keep adding servers. Scale up is a basic strategy underlying Windows Azure services. So you can keep adding servers, but that's not how it should be. You should code your application well so that you scale only when you need, because when you scale, you pay money. So this mindset is wrong. You see how to change this now. scale comes with price. As I told you, add more servers, you add more services, you're going to pay more. Right now it's hourly rate for almost all the services, plus the amount of storage that you can use. So, quickly check the first is how many of you have used Azure services before or built Azure applications? Okay? For those who do not have a lot of experience, you can ask questions. But maybe some of the terminology may not be familiar to you. I'm talking about cloud services and workflows. You can always ask. Okay. So, right from the design phase, you have to take care of a few different things. So, these are the areas that you generally use. You build web roles, you build vector roles, and then you use the storage only. Use cache, use SQL data. These are the four, most used things in the test now. Right? So when you design your applications, you make sure that you make best out of these. When you are writing these services, you write it in a way. Let's delve into each of them one by one. Looking at compute, what are the worker roles? So, how many of you have here before? Okay. Threading, multi-threading. That's just the way it is. Somebody is multi-threading before? Okay, so as of 4.1, right? We have a library to actually write multi-threading. To have a library that makes it very easy to get different threads, execute your operations on different threads. There's the underlying mechanic. The library handles it. That's very important. You don't have to do thread synchronization and all that good stuff. Now, when you choose your VM, right, you either choose one of these. Mostly for during development, you go with small size, which is scale notebook. But for deploying, you generally have medium or large, different workflows.
Now, how you use those codes so that you do not end up with a slow application, or if it's a worker role, you do not end up with worker role doing less amount of work. For example, until 2 months back, I was working on a big application that has the requirements for processing around 110 messages per second. Those messages are coming to our application, and we would like, if we don't want messages to stack up there in our queues, we should be processing at that rate, 110 messages per second. So we had kind of a couple of medium worker role setup, but we were still reaching like 20 messages per second. We used 30 messages per second, processing like 2 worker role instances. And what we did, we parallelized the whole thing and moved to large, like 4 and 3, instead that we had 12 cores then. And it came to around 65 messages per second. That was the only change we had to do. Just parallelize our code, that's all. The code never changed because we had it refactored out. How the thing changed, you create multiple threads. And we started extracting the max out of the worker role we were using, the cores we were using basically. Also, async pattern. This is new again. How many of you have used it? Async await. Okay. Before this, there was begin request and request. I think everybody would have used it. If you have used WCF with Silverlight applications or any client applications. So this is again a wrapper on that, makes it very easy to write asynchronous code. So if you have IO calls, like you are downloading a blob, for example, so that's a network call, right? Your application is like still waiting on that call until that returns, right? It's blocked. So So you can use a sync pattern. It goes to the next line. It doesn't wait there anymore if you use a sync. And when that call completes, takes out the remaining portion of the code and puts in a lambda and in a delegate, executes later on. Your application can continue processing. There's something again we use in our application to increase the throughput. Yes, the best pattern is to use both of them in conjunction. You may have, for example, a table. As your table with like 1,000 of entities, you get them like 2,000 of them, parallelize it, and for each entity, for example, you need to do some operation, right. When it's a network call, service, and you can use a sync there. Let me show you an example on this one. Is it visible? Can you guys at the back read it? No? Okay. Now? Okay. I'll go through it part by part. So here, again, if you have used latest Azure SDK, we have this table query used to query Azure tables. I have a table called post. This could be a simple application like Yammer. You keep on heard about Yammer? Yammer, the corporate social platform called Yammer. Okay, again, let it be an application. Let me describe it. You're building an application that you can, as a PaaS application, platform as a service, and that different companies can use. Right? They can create their account there, and then they can have their employees there. They can have communication between them. They can upload photos. They can upload documents. All that stuff, right? And assume you are building it on Windows Azure, hosting an application. It's a simple, a normal ASP.NET application, but you are hosting on Windows Azure using Azure Tables as the backend, right? So what you're doing here, suppose like here an account for Neurasic, and it's been like, we have been posting emails, we have been, Neurasic guys have been talking around, right? So I'm querying that table, and this kind of gives me like 5,000 results in this query. Now, if I use a simple for loop, it's going to go through all of the 5,000 and say I have a large VM, just 4 cores. I parallelize that. This is what I was talking about, parallel for each. I think, yeah, you used it before. So what it does is manages, creates, looking at the number of cores that are there on the server, creates threads, and takes out the body, gives to each of them, right? So now it is like partitioned. It does data partitioning. If I had like 2,000 rows, ideally it would make a partition of 500 each, and now we are parallel processing 500 rows. Otherwise, you would have been doing 2,000 sequentially, right? Again, for each row in that table, for example, I have an image URL and I need to process. For example, we upload a lot of images, right? And I need to create thumbnails out of them. And that is a heavy operation. First, I need to get those images, download from the blob, for example. This is what I'm doing there, that code is doing there. You are taking from the table column property, you're getting the image URL, you're downloading it, and then putting into memory stream to really, create thumbnails out of it. You have to process it, you have to make it byte, chunk it out into bytes, and then create thumbnails. So there is a method on blobs, download to stream async. So library internally gives you all the async methods now, so that you can, in your code, you can use that code out there is not blocking again, and returns as soon as the line executes. And whenever that whole, maybe a 2 megabyte image is downloaded, the rest of the code will execute, right? Until then, it will go to next item, process it, get the reference, and do rest of the things out there on top. So that is the benefit of it. You don't need to wait on that statement download to stream. First was you chunked out the items into 500 each. Now you're parallel processing them. First improvement, right? Second, you're using a sink there. You're not waiting on anything. Maybe network is slow. Maybe your net connection is slow. Now this is executing in a virtual. Sorry. Maybe that image is big. It takes time, right? It takes maybe 2 seconds. You don't want to wait for 2 seconds. Pass it on. Whenever it returns, you execute the rest of the stuff. You do your processing then, right? So these are the two main things you should do when you're writing cloud services, particularly worker roles, because they do your heavy lifting most of the times. We can still use a sink. ASP.NET MVC has async controllers, right? The latest version, 4 has async controllers. The goodness of sync is out there. You can use async controllers. They will not block your request. For example, your website takes a lot of requests, heavy load, right? A lot of users. So they have given you async controllers. Makes a request, frees up the request for other requests to come in. It doesn't block the request, it doesn't block the thread, because in ASP.NET model, you have one thread created for every request. So the threads are freed up if you use the same thing as this. Okay. So that is for compute. Let's look at the storage. This is where you can have a whole lot of improvements. I'll go through one by one through each of them. Disable Naggle. Heard about this algorithm, or ever use this class, Service Point Manager? Okay, so this is the guy who manages your outbound connections. Azure Storage service is exposed as a REST API. Essentially, when you use storage line libraries, you make REST calls at the end of the day. They give you .NET wrappers over it, but they are all REST calls. They are outbound REST calls. This guy, Service Point Manager, that manages those calls and manages how many instances of a service point are going to be created for each calls. For example, you're making to the table service call, URI remains the same. So for every call, like I had 2,000 calls there, the parallel for each, right? I had around 2,000 calls. So it's not going to create a new instance of the service point class, and every time set up everything before making the actual call. This guy is going to cache it up and recycle the same instance. That properly you can set up, but Naggle is something else. What happens is, if by default, this property use Naggle algorithm is true. You can actually take notes so that you do not forget when you do actual calls, right? When it makes a call, it sees the message size is too small, right? It doesn't make an outbound call. It waits for another call, and until the TCP window is full with a sufficient chunk of request size, then makes all those calls. So, for example, small calls like queue messages could be very small. Just maybe you're pushing a name, say 50 bytes or so. They will be waiting there until when the rest of the calls come, and then all the calls are sent. This was for maximizing bandwidth usage, this algorithm. Whenever there are chat applications, stuff like that, every letter used to get sent. So this algorithm, if you set it to true, it waits for the whole word to be typed and then it sends. That thing is in general true in .NET, but in case of Azure, this downgrades performance a lot. If you're making a lot of universal service calls, because in case of queues, like the scenario I described, we were processing 110 messages per second. So that was a lot of calls for us. A lot of calls. We were actually getting so many messages, and then we were pushing information at that rate. So remember to set this to false. This improves your outbound call efficiency and reduces latency. Second thing is expect 100 to continue on the same class. You're talking about the same guy who manages your service connections. What this does is every call you make, every REST call you make out, say to the table, Azure table service, it goes and checks whether this is a valid request, and then the service returns a valid token. When it's validated, then the actual data is sent. Now we don't want that if you are making a lot of calls. A high load application, a huge number of calls per second, we don't want that. We don't want to go check every time my request is valid or not, and then finally send it. Set this to false. So no matter what, it'll send the request. So we are saving one request per request. We are making two requests actually, if you set it to true, or rather it is set to true by default. Set it to false, we are down to one request. So that improves efficiency again on your outbound calls. Default connection limit. This is actually, if you have build workers before, this is, you would have noticed this is set to 12. This is the number of connections that will be open at any point in time. It's like connection pool thing. Now, default limit is 2 for .NET. For ASP.NET there is an exception. It is to 10 because it has to manage a lot of connection, a lot of requests come in all the time. But for worker roles, default limit is 2. So if you are again making a lot of calls, it is only 2 calls that can be active at a time. For example, your queue service is slow. For example, you have 2 million records. Not even that much, I would say 50,000 records in your table, and you are making calls. You made 4 calls to the table service, right? 2 of them are taking time to return. So the rest 2 are blocked. They will not be made. They will not be sent out. Those requests will not be made. They will wait until the previous 2 requests return, and then there's the goal. That's why if you have higher requirement, you can set it to, let's say 200. Now everything will be sent. You're not waiting on. You have these many threads in the pool that can be sent. The request that can be sent. Okay, so compute and storage. There's no point keep them as close as possible. Ideally, create an affinity group, assign the same thing to both of them, because this will reduce your the time taken for outbound calls, data exchange, because your compute is your, again, web and worker roles. They need data, they consume data all the time. Best thing, keep them as close as possible. Keep them away. Your network latency will be high, and then you'll have slow processing in worker roles or slow response in your web roles. Okay, scalability targets for each service. Any what are these? These are what Windows Azure team proposes. This is what we support today. These keep changing, but you should know them. That makes you make better decisions about how my service is going to perform. For example, let's look at some of them. Is this visible? The back? No. Okay. Okay. So storage account is the top level container. So the underlying concept as your service is partitioning. They scale out on the basis of partitioning. Everything you create goes into a container or a partition. Once you're done with that partition, you have exhausted the limits of that partition, you can go and create another one. That's how Azure helps you scale or makes you scale. Right? Top level for storage is a container. Sorry, a storage account, as good as a container. A storage account that you create, and it can support up to 200 terabytes of data. These are the proposed stats from the Windows Azure team. How many requests it can take? 2000 entries or messages per second. You may be stuck. If you don't know this, what you need to do is, if you have crossed this limit, your application is very high load. If you have crossed this limit, go create a new storage account. Start using it. make your application configurable to use that, or on the fly, when you reach these limits, you go and create another storage account, right? You may be wondering why my application is not performing. It's not infinitely scalable just on a single storage account. That's the limit on a storage account. By default, geo-redundant storage is true, which means that your data is replicated in a region across data centers. That if you want high durability for your data, you don't want to lose it. If in a rare event a data center crashes, something like that, it catches fire, you don't want to lose your data. For that, geo-redundant storage is true, but that also makes your bandwidth low. You can only the application can only take request at a rate of 5 gigs, and users can read only at the rate of 10 gigs per second. Now, if you disable it, you go and almost double the ingress bandwidth to 10 gigabytes per second, and egress to 15 gigabytes per second. If you don't really want so much durability for your data, right? That's when you create your storage accounts. There's something to choose, and you can go and actually update that flag. Okay. Second thing is your blob, table, and queue limits. You have a limit of 16 MB per second or 5 requests per second for blobs. Again, that can be crossed. You have to go and create another blob partition. Now we have one level down the storage account. We are into blobs, queues, looking at their partition limits. So a single blob can handle only this much. You are uploading a lot of image in this. This is your limit. Similarly for queues, 2000 messages per second. You cannot read faster than that. Now that's what when I come to queues, I'll have recommendations on how to circumvent these limitations. Similarly, table partitions, you have again 2000 entries per second. You cannot do it faster than that as of now. Maybe they come up with a better service tomorrow as your team releases something else which extends these limits. Okay, let's go to, these are the general guidelines that apply to storage in general. Let's look at each of them in particular now. The table storage. The most important decision while creating Azure tables is the choice of your primary keys and the row keys. Sorry, the partition keys and the row keys, which is a combination of those is a primary key. Actually, a partition key is a single partition. You are guaranteed to have all your entities in a partition on a single server. What that means for you is when you make requests, your requests are not going to go to any other server based on a partition key. Now this gives you huge performance benefits. You can have thousands, hundreds of thousands of records all in the same server. That is guaranteed if you choose if you query based on a single partition. They don't split across servers based on how much data it is. If they have used a smaller VM initially and your data is growing, move that data to a new VM which is larger. But you're guaranteed to have all that data in a single partition on the same server. Now this design is enforced by what kind of queries you are going to write. Whenever you create Azure table entities, you need to look at the kind of queries you are going to write eventually. Your queries need to be fast, right? Based on that, you will choose your primary keys and the row keys. And the row key is again unique across a partition. For example, right there in the example I'm showing you, Newdesic.com as the primary key. I could be handling data for a lot of companies, Newdesic, Microsoft, Deloitte, Accenture, right? In the same table. And I can partition it on company, so that I get an isolation. All my Neo26 data is all on the single machine, right? And it's partitioned well. Now I need some uniqueness inside that container, inside that partition. Then I choose my row key, right? And then when I query, the fastest is the point query. So eventually, when you use Azure tables, you are going to write queries. You're going to query data. There's no denying that fact. The fastest query is the point query. I'll give you just single row. You know the exact partition, you know the exact row key. Second is, notice partition key is always there. Second is, you have a range of rows you want, and you know the partition key. Okay, inside Neo26, I need the information for, say, so many employees, right? Right? So you can put a range on row key. That's unique across partition. That is still fast, but not as fast as the point query, the first one we have. Now again, you want data across companies, right? And you're okay with getting a little slow. Now what this will do is, you're querying on partition key and giving it a range, right? Now you're querying, hitting different machines, different servers physically. If you imagine that your data is always stored on a physical machine, right? In Azure data center. Now you are hitting different machines. Now it gets slow. It's gotten slow there. Now, and if you write, like you write your SQL Server queries, like this thing is equal to this thing, doesn't work well in Windows Azure. That's not how it is designed. That's not why it is. It will be living throughout on all the servers, the data is there. Every possible row. You're not narrowing it down by row and partition keys. So that is going to be very, very slow. And again, same thing with the just row key, because it doesn't know. When it knows the partition key, it knows that this machine I'm going to look at. This set of data I'm going to look at. And that gives us that chunk, and then you can filter it out. Right? So, most important decision there, your partition key and the row key, decision of that, what is that going to be? For example, in this scenario, I kept companies, I wanted that isolation, I wanted that partition. And then your queries. Never do like what you do in SQL. That's going to perform very badly. It's not at all recommended. Okay. Some more things on tables. Azure tables. You do upsert. This is near in the library. Upsert is look at the word. It's a combination of an update and an insert. It's a combination of an update and insert operation. What you generally do for update, you get the data and then you update it and then you send it. Then you fire an update operation. And it actually gets the data, that operation, and compares it. It checks for the existence of that entity. Otherwise, that call, the update call in Windows Azure Table Storage API is going to throw exception. If that entity doesn't exist, if you have written Windows Azure table queries and try to update on a non-existent entity, is going to throw exception saying this entity doesn't exist. What this lets you do is avoid that call to check whether entity exists. So you are again making one call instead of two. Do one insert or replace, which means if the entity doesn't exist, it's going to insert it. If it exists, it's going to blindly replace it. And it's again going to compare on primary and row keys and blindly replace it. Whatever was there is going to be replaced. Doesn't care whether it existed or not. Second, if you don't want to do a blind replace, you do an insert of merge. What this does is, if the entity exists, it's going to keep those properties intact and add the additional properties. So if you look at Azure tables, they don't have fixed columns. Or a flat design. You can use as many columns as you want on the fly on the same table. You can have an entity with 5 properties, and then you can fire a query to insert an entity with 10 properties. Very much possible. That's not relational. You're not bound by number of columns you have. Entity projections. This is again new. What it lets you do is, say you have a table with like 200 columns and you want to update something, label of it. You have to get all those 200 columns, all that information. You don't need, you just need to update one property. This lets you do that. Query a subset of properties. Again, something like SQL, you write, just get me this. This gets you only those properties, update them, send them over. How does it help? Bandwidth, saves you bandwidth. You're not downloading data that you don't need. Right? Again, in your development scenarios, you will not feel the pinch of bandwidth and the performance and all that. When you are building high load applications, then you will feel the pinch. Right? Then you will see this is not performing, this is too slow. Right? So if you take care of these things from the beginning, they are in your head. You have this checklist. Okay, this is how I'm going to do. You'll save a lot of time later on. Like you can save months spent on just tuning performance. Right? When we start developing, we just focus on features. Okay, got done, and just give demos to clients, customers, which passes because we never do performance tests. And when it goes to actual production, and when the actual users start bombarding it, then you see that it doesn't perform as it should. It was written somewhere. We've committed to it'll take so many requests per second, the response time will be so good, we'll be able to crunch so much data in so much time, and then you go back and start tuning performance, reading on performance, that kind of stuff. And then finally, if you have not written your code very well, you can end up spending a couple of months just doing performance tuning. So, if you're aware of these things in the beginning, well, you don't need to have that headache. You don't need to worry about those things. Okay, this is for tables. Let's talk about blobs. Again, blobs are high capacity data stored for you. You can store email, you can store virtually any kind of data. It's a high capacity file system essentially, right? And so any kind of files and blobs. And then what you do is you have to download those files. You have to read that information. They are big chunks of information. What you should do is, instead of reading just about everything, you do a range reads, a range of information, narrow it down. This is what you need. And then also, if you have used the client API for blob service or storage client library, or what we mostly do is just do a download blob. That's not optimal. That's not what you will need always. Maybe you just need a little bit of information on that blob. What's in the what's the metadata? What's the name? What are other attributes? You just query those things, and the API gives you those things. Most times we are just not aware. We just do a download blob, and then we start reading properties. Right? So if you don't need that stuff, don't do it. That again hits you on the performance side. While uploading blobs, similar with header requests, again in the header, you have a lot of information. It's a REST call. When you make a call, you get back the response. It gives a chunk of information about the blob in the header. Okay, if you're say uploading very huge blobs, say videos or big images, you have the ability to upload them in parallel, as we talked about initially. You also have the ability to upload a single blob in chunks, parallelize them. Like I have like 8 codes available, and I'm uploading the same blob, cut it down into chunks, and upload it. So that becomes X time faster, right? Uploading the same thing by breaking it down. It's not just you're uploading a single file and streaming it up. So as long as the last byte goes, it's still waiting. If you parallelize, the storage client library gives you ability to break it down in chunks and do a parallel upload. That's what we're talking about when we talk about parallel uploads. That brings me to, you have, when you use the blob API, you have two kinds of things. You have blobs and page blobs. So if you don't worry about, reading information randomly from a blob, use blobs. That is again the name says you're uploading block of it, or you're reading block of it, downloading a block of it. That's why it's called blob. Page blobs takes a chunk of information to an. Okay. Some things on blobs. Queues. Queues are particularly important for high throughput scenarios. In a system like ours, you have a lot of messages to process. In fact, if you have kind of task-based thing, a task gets queued up in a queue and worker goes and looks at it. This is what I got to do. For example, we're looking at creation of image thumbnails, right? My company approved a lot of images, right? Now I need to create thumbnails to be displayed on a page. So our worker role will essentially, what it will do is you'll queue those requests as messages in queues, and then finally worker role goes and picks them up, picks the images and starts doing. We talked about Nagel earlier. This is more prominent in queues because you have small messages here. This kind of blocks you from sending a lot of messages. So while reading, the general tendency is to read a message, queue.read message. That's not optimal. Not optimal at all. You do a batch read. There are two benefits to this. One is performance, second is cost. What happens is, in the queue service, you pay for every request you make, every transaction, right? And it's the same with table and the same with blob. If you read one message at a time, you are making like a lot of calls. For every call you are paying money. Now if you do a batch read, 32 is the limit as of now. You read that 32 messages in a batch, you pay for one transaction. Cost benefit, performance benefit, you don't make 32 calls, right? Two benefits you get there. But when you read message, you generally do well, you make them invisible. If you have done queues before, you make them invisible so that nobody else picks it, because you have picked up, your worker role typically picks it up for processing. So you make them invisible to other worker roles. Nobody else is going to process. Now, if you say crash on, you get 32 and if you crash on, say, 4th message, rest 28 will be, your application crashes, rest 28 will still be invisible. Nobody can pick them up and process. So in that case, that's a caveat. Use error handling and immediately go and make them visible, right? Or you can still continue processing. Don't write code just like the application error is not handled, and you will have all your messages sleeping there, waking up after the visibility timeout is over. Okay. Design application for updates. Don't do a get and delete. Again, saves you calls, transactions, costs, and again 2 calls instead of 1. Do line updates. I'll go and log, will update that message. That's it. That's all you need. Most of the times. Now again, we talked about scalability targets for queue service, 2000 messages per second. Now when you hit that limit, what do? You should have an ability in your application to create multiple queues so that your different workers can actually look at different queues. If you're doing 20,000 messages per second, this queue will stop. It will start throttling. It will not give you more messages than that. So for that, you should have more queues. You should have that planned in the beginning. And that you have to do dynamically. So that again requires thorough planning, coding. If you need performance beyond that kind of performance, right? That should be designed from the beginning. You cannot just go and manually add. Today, I'm not handling 20,000. My load increase, I'll add one more queue. Doesn't work like that. You go and change your code. That should be in the design. Again, round robin, the worker roles can do. This queue is getting slow. It's kind of blocking. Go to next queue. You have the same messages there. Duplication. That is again for avoiding throttling. It doesn't give you so many messages because it's already getting so many requests, which is beyond its limit, right? So That was on queues. Before I moved to caching, any questions so far? No? Okay. All right. Caching. So you would have used caching in your ASP.NET applications or any other applications, have you? Or used Azure caching for that matter? No? Okay. So this is again, caching is for saving a lot of outbound calls, data calls. A lot of the data doesn't change. So Azure gives you right now 3 flavors of caching. One is in-role caching, other is a dedicated role caching, and third one actually is deprecated, which was a shared cache. No more there. So when you are using caching, it's very tempting to not spin up a separate worker role dedicated to cache. Very tempting, since you have the option there. What you do most of the times is you go and choose that 30% of my worker role or web role, give it to cache. But when load on your system increases, keep pushing objects into cache, and that 30% exhausted, and then your application starts to crash. Also, throughput is not that high. Cache is for giving you data very fast, right? And when you're making a lot of requests, it's not dedicated, because that same machine is also, when you use in-role caching, it means is if you have a web role, you say use 30% of my web role's CPU or memory. Say it has 8 gig and 30% of that for cache, right? It's the same machine hosting your web app also, and it's the same machine serving cache requests also. Again, it exposes a service on the cache to serve up the cache. That gets slow. Don't use it. It's fine for development. High load scenarios, production not recommended. Go for dedicated cache. You'll get slow if you use in-role caching, right? Again, for high throughput, use multiple instances. Cache also has its limit. Cache service starts to crash, won't give you data if your requests are very high. For example, in our application, we had like a couple hundred requests per second, for example. Like I talked about, we were processing so many messages. I would say I would typically had, in my scenario, my application around 200 requests per second. My cache, I had just one worker role initially. Started crashing. Well, what we did was create another instance. Now we have 2 instances serving up. So load balancing happened, and the cache went fine. We increase the load again, 2 will not find. So we have to tune this up for our cache to perform. Also, we'll come to error handling. Data cache factory, when you use the API, this is the guy you will be using. This is the entry point. It gives you the cache manager actually. Don't instantiate again and again, because it's going to create new connections. That is again slow. That is slow. Keep a static instance of data cache factory. Let it manage. If you do new data cache factory every time you make a request, that will be slow. You're not getting much out of cache. And yes, when there are a lot of cache can also fail. So use retry logic there. We'll see an example of this. There is a very good guide released by Microsoft, Cloud Design Patterns, that you can Google up. It's called Cloud Design Patterns. It has around 24 patterns, if I'm not wrong. So the best practice again, different patterns you can use to build cloud applications. The name is Cloud Design Patterns. I think I have it in references too. Don't maintain a state in your cache provider. You will generally write a cache provider that keeps your cache. Don't maintain a state there, because as we talked about previously, if we do parallelism, this thing is going to override a lot of things. Multi-threading is not going to handle. So not recommended. Don't use a state. For example, you are keeping variables out there, static and all. Don't use that. Let me quickly give you an example of cache size pattern. The diagram on the right, I don't know if it's visible. Okay. over here it is. This is how your cache should be designed. What do you do when you write this? Look whether the item is already in the cache. If it's not, fetch from the database, store a copy in the cache. Okay? This is what that one of the patterns related to cache says. And the kind of code you're going to write is this. There's a method written that gets my entity asynchronously. What it does is, while storing items in cache, you have cache keys. Based on that, you have values. What it does is, first looks into cache, it's not there. And that may even throw exception, so you need to handle it accordingly. If you look at the update pattern, you look at the whole design pattern. I have not tested out the whole code yet. There is difference. For update, you're not actually updating; you're just clearing up the key. And again, this flow follows. Yeah, the strategy is going to be the same. The kind of code you write there, the try logic and all, slightly changes with the API. I would recommend looking into that pattern. Overall, from the high level, strategy is going to be the same, right? Because you look in the cache, you don't find it, but when you look at the code, that looks slightly different. Based on, again, it's based on the API they have released for the cache, exception handling and all, and they have retried all logic built in. There is a good Enterprise Library 5 released a good transient fault handling block. That's what it is called. Lets you handle these faults and all. So it tries for you, so you don't have to write retry logic and all. If fails, do this. Lets you do everything. Check out that transient fault handling block also. Okay, like 6 minutes to go. Let's see how we manage some of the performance counters in Windows Azure. Coming out of Visual Studio. Performance counter is what it gives you how many reads and writes are occurring for you. I had a small application deployed to Windows Azure. So, if you have deployed applications to Windows Azure before, you look at, you have these configuration files out. Sorry, my Visual Studio is not there. Okay. Sorry, this is not duplicated. Okay. So, hope you can see this. If you have deployed applications to Azure before, you have these configuration files where everything is configured. Now, for what we are talking about, performance counters, logs which tell you information, how much CPU cycles are used, how many requests per second is your application handling, stuff like that, right? This is monitoring, diagnostics. So for that, you'll have to import a module called diagnostics module when you deploy your applications. Without that, it's not going to work, because what it does, it logs all that data, it monitors your application deployed on a server, a VM. It monitors all that is going on and it starts logging into a Windows Azure table, a logs table. So if this module is not imported, it will not install that monitoring agent out there on the virtual machine. First thing is you have to import this. Second thing, you have to configure the connection string for the diagnostics module. Here are your configurations. Where it's going to, what is your storage account? So I have created a storage account before. This is the connection string that it would do. And when you deploy application, I can show you my storage account actually quickly. Oops. Number one. Second is the table where it goes. Now, how much time I have? Okay, I'm almost done. Last thing I want to show is where your data is going. Performance monitor logs, the counters. This table got bad. Windows Azure performance counters table. here all your data will be going based on what you have configured. Again, there's a missing link here. This is the file, diagnostics.config file. By default, there are a lot of entities already out there for you. You can add more counters if you want. I actually configured for this one. Whole lot of counters you can use. You can use available bytes. For ASP.NET, mostly there is stuff like how many requests per second I'm handling. For worker roles, available bytes, available memory, all that stuff. And then on that table, you can actually see these logs. Read that information by the name of your counter, and these are the values. Request per second, how many bytes are available, how many bytes I'm using, stuff like that. Okay. Last thing, I think I have summary left. That's it. Okay. To summarize, let me just share this again. To summarize, performance is not you should start doing in the end. You should do it from the beginning. Design for it. Go through documents, go through the recommendations. Maybe you have not done things when you work on Windows Azure applications. Use that stuff. Know your tools in your platforms, like the scalability targets I showed you. That is what the service supports. There is a maximum that service supports. Now, if you get stuck, you need to have a plan. How am I going to scale my application? How it is going to perform better when I reach these limits? Parallelize where you can. New libraries, parallelism, and async. Do all your I/O on async. Whenever you need to make an outbound call, get a file, download a file, or save a file, stuff like that. Even now, even table entities support async calls. Even queues support async. Use sync whenever you can, whenever you suspect it's taking more time. And use cache heavily. That gives you a huge performance boost. Nothing like cache. You can have different kind of expiration policies, but nothing like cache. Nothing runs faster than cache. These are some of the references. Cloud design patterns, the last one I already talked about. There is how the services are designed. If you know the internals, you will write your applications better. And best practices for large scale services in cloud, I can share this with you. If you're interested, just contact me after this call. That's pretty much it. Any questions? Thank you. Yeah. Thanks a lot.
Thank you, Pushpendra, and I thank everybody for being a part of this day, GIDS.NET Day. We look forward for your feedback, so kindly post and tweet your messages with #GIDS.